Next we are going to start now the next lecture, lecture 3 of chapter 1, class 12th mathematics, relations and functions. So we know the definition of the function. It is, we are given two non-empty sets A and B. Then a rule F which associates to each element x of A unique element from B. It is called a function from A to B. We have also seen in our previous class, in class 11th, that function can be seen as a special case of relation, that these are special kind of relations. So for more details, you can refer to the video of functions from the class 11th. Now in this video, we will talk about various types of functions. The first we have, it is the many one function. So a function from A to B, f from A to B is said to be many one if two or more than two elements in A have the same image in B. I will explain you these one by one, particularly with the help of the arrow diagrams. So when we are talking about a function, we are saying we are having two sets. These are non-empty sets A and B. We have some elements in A and we have some elements in B. What is function? We are saying for each element in A, we associate an element of B, and this image, it is unique. So we are saying, if suppose in this particular case we draw another relation over here, this is we are talking about, these are the elements 1, 2, 3, these are the elements A and B. Now what is happening over here, that this one is having two images. We are saying if this is the function we are talking about, this is not the function, we are saying there is a relation R, and the relation R is such that one is related to A and one is related to B. And what is happening over here, this one is having two images. So we are saying this is not a function. This is not a function when the element of A has two images. So first thing is, we are sure that every element of A should have an image. If suppose we have an element 4 over here which is not having the image, this is not a function. So these are the two conditions to be satisfied for a relation to be a function. First is that every element of A should have an image and every element should have a unique image. Now one thing is clear, that we are talking about the function, that these two conditions, these are satisfied. Now the first type of function we are talking about, it is many one function. So now we are having this set A and we are having another set B. In A we have elements say 1, 2, 3. Over here we have elements A, B and C. We are saying 1 is having the image A, 2 is having the image B and 3 is having the image B. Now in this case, this is a function. Why? Because every element in A has an image. There is no element over here which is not having an image, and every element in A has a unique image. It means 1 has image A, 2 has image B, 3 has image B. Unique image means that it is not like this that 2 has two images. It is not like this that 2 has image 2, C and B. Now when we are talking about many one function means that two or more than two elements in A have the same image in B. The image of 2, this is a function, the image of 2 is B and that is equal to the image of 3. So these kind of function, these are called many one functions. The next type we have, it is one, or it is called an injective function. You must remember this term, injective. It is commonly used. So when we are talking about injective function, it means we are talking about one function. So one function is A function f from a to b is said to be 1 1 if distinct elements in a have distinct images in b. It means this function, it is not 1 1 function. For 1 1 function, again we are considering the elements over here. It is 1 2 3. This is a, b, c, and say it has element d also. We are saying 1 has image a, 2 has image d, 3 has image d. Now what is happening over here? First of all, every element in a has an image. Second, every element in a has a unique image. Now, when we are looking at the elements of b, this a has a unique pre-image, b has a unique pre-image, and d has a unique pre-image. So these kind of functions, we are saying these are 1 1 function. That when we are saying this b, there are two pre-images of b. So this is many one function. When there is a unique pre-image for every element of b, then that function is called 1 1 function. So what we are saying is that fx1 is equal to fx2. This thing implies us that x1 is equal to x2. It means if we consider any element from b, then yes, suppose we are saying there are two elements x1 and x2 which have images f of x1 and f of x2 which are equal, then both these elements x1 and x2, these will be equal. This condition we are talking about, this will be used when we will be proving that a function is 1 1. This will be more clear to you when we will solve some problem in our next slides. Next we have is onto or surjective function. So onto or surjective function means a function f is said to be onto if every element in B has at least one pre-image in A. The next type of function we have, it is into function. Into function means that if there exists even a single element in B which is not having a pre-image in A. Now look at this C over here. This C over here, we are not having any pre-image of C. Look at this C over here. It is not having any pre-image under this function. So we are saying both these cases, in both these cases we have an element which is not having a pre-image. So we are saying in both these cases, this function, these are into functions. And we are talking about the surjective function. Surjective function means we are having the element 1, 2. Over here we are having the element say A. So we are saying this 1 is mapped to A, this 2 is mapped to A. There every element in B, there is a pre-image in A. So this kind of function, this is an onto function. It means, what is the definition of onto function? That every element has pre-image means that range of this function that will be equal to the codomain of this function. These will be more, these all conditions that are given over here, these conditions I am talking about, these will be more clear to you when we will solve some examples. The next thing we have is a 1 1 onto function is said to be a bijective function, or it is said to be a 1 1 correspondent. So a function which is both 1 1 and onto, it is called a bijective function. Next we have is many one function. So this example is given over here. We are saying why it is many one, because the image of this element -1 is 1. The image of this element 1 is also 1. So there are two elements in A which have the same image in B. Or how you can look at this condition is that if we look at the pre-images of 1, there are two pre-images of 1. So this function is many one function. Further, if we look at this set B over here, every element in B has a pre-image. It means this function we have, it is the onto function. This function is onto function because every element in B, it has a pre-image. Next, suppose we are talking about the set function which is defined on the set of natural numbers, and it is defined like fx is equal to 2x for all x belongs to n. Now we have to check whether this function is 1 1 or not. Now what we have said, that a function f is 1 1. This thing is implied and implied by, if we are saying that f of x1 is equal to f of x2, this implies x1 is equal to x2. So to prove that it is 1 1, it means we are saying that every element in B has a unique pre-image. So suppose we are saying that in B, in A we have two elements x1 and x2 which have the same image in B. What this thing means is, we are saying suppose in N means we are talking about in set B we have two elements x1, in set A we have two elements x1 and x2 for which the image is same. We are writing there are two elements x1 and x2 such that f of x1 is equal to f of x2. By the definition of the function, we have this is equal to 2 times x1 is equal to 2 times x2, and this thing implies us that x1 is equal to x2. It means if the image of two elements is the same, then those two elements are same. It means that this function f of x1, this is a 1 1 function. Next example we have is, let n be the set of natural numbers and e be the set of all even natural numbers. We have defined a function f from n to the set of even natural numbers, and it is defined like fx is equal to 2 of x. Now we have to prove that this function is an onto function. It means we have to prove that the range of this function, that is equal to the codomain E. The range of this function, it is equal to the codomain E. Or second thing we can prove is that we consider an element. Say we are saying there is an element we are considering, it is y, which belongs to E. Then we have to prove that every element has a pre-image. We are saying for each y which belongs to the codomain of this set, we have there exists an x that is equal to y by 2 which belongs to n, such that f of 1 by 2 of y, that is equal to 2. Now we have applied the definition of the function. It is 1 by 2 of y, that is equal to y. What we mean to say over here is, we have proved that for every element y in the codomain, there exists a pre-image in n. This is equivalent to proving that the codomain and range of this function, they are equal. So we have proved that this function is an onto function. Next we have, it is an example of an into function. We are saying that a is equal to the set 2 3 5 7 and b is equal to the set 1 0 1 3 5 7. We are saying f is a function defined like f of x is equal to x minus 2. So if we list the elements of this function, we are substituting x is equal to 2. We get f of 2 is equal to 0, f of 3 is equal to 1, f of 5 is equal to 3, and f of 7 is equal to 5. So what is the range set of this function? It is 0, 1, 3, 5. What is the code main of this function? It is this B. This is the range set. Both of these are not equal. We are saying this set 0, 1, 3, 5. This is basically the proper subset of the set B. It means the codomain and range, they are not equal. It means there is an element 7 over here which is not having, 7 is not having a pre-image. So we are saying that this function is not an onto function and it is an into function. Next, this figure shows the some facts about 1-1 mapping. So we are saying 1-1 mapping means we are talking about injective function. So every element of this set B, it has a unique pre-image. We are saying this 3 is having the image 1, this 7 is having the image 3, 11 is having the image pre-image, not image, it is pre-image, it is 5. So this function is an injective or on 1-1 function. Now it is important to note over here that this 15 is not having any pre-image. It means this function is not onto but it is into function. So we are not talking about these cases over here. So when we are talking about a function is injective, we are not considering this element over here. We are just talking about that every element over here, it should have a unique pre-image, that it should not be like this. We are saying it should not be like this means it should not be the case like this, that 1, 2 and 5 is there. So it is A and B is there. A is having image this, A is having image 2 and this is having this. So this function is not an on 1-1 function. So this thing is explained in our next figure. We are saying over here this P has pre-image A, it has pre-image B and it has pre-image C. Similarly, in this case this Q has the pre-image B and this Q has the pre-image C. So we are writing the pre-image of this Q, they are B and C, so it is not unique. So we are saying these function, these arrow diagram, these represent the function which are not 1-1 functions. Next, we have given two methods to check whether a given function is 1-1 function or not. So we are saying the first method, it is the graphical method. So a function is 1-1 if and only if no line parallel to x-axis meets the graph of the function at more than one point. So we are saying, suppose we are talking about the graph of the function fx is equal to sin x and it is plotted between the region minus pi by 2 to pi by 2. This is the graph shown. So we are saying that no line parallel to the x-axis meet the graph of the function in more than one point. So we have drawn a line over here. When we have defined the function, we have done over there the parallel line test. We are saying this is the graph of the function. Over there we have drawn a line parallel to y-axis. This is for the definition of function. When we are talking about the 1-1 function, we have drawn the line parallel to x-axis. If it cuts the graph of this function at only one point, wherever we draw this line, it only cuts at one point, then we are saying this function will be 1-1 function. Now suppose in place of this, I am drawing the graph of sin x. Same the region like this, we have drawn the graph of sin x. This is our x-axis and this is our y-axis. Now what will happen over here? If I will draw a line parallel to x-axis over here, it is intersecting at this point, it is intersecting at this point, it is intersecting at this point. So we are saying if we are writing the function fx is equal to sine x, and we are not restricting our domain to this portion, this is for all x belongs to R, then this function is not 1 1. So it means for a function, when we are checking whether a function is 1 1 or not, it is very important to see that in which domain we are talking about. As in this case, when we are talking about x belongs to R, this function is not 1 1. When we are saying x belongs to this interval minus pi by 2 to pi by 2, this function it is 1 1 function. The second method to check whether a function is 1 1 or not, it is the method of derivatives. So it is how we have explained this, to find whether the function is only increasing or it is only decreasing in its domain. So a function, if it is only increasing in the domain or it is only decreasing in the domain, we are talking about, suppose any function is there, this is our x-axis, this is our y-axis, any function is there, this is our x-axis, this is our y-axis, this is the graph of an increasing function. Some function will be there that is increasing function, its graph will be something like this. It may be anywhere on this plane, but it may be something like this. So we are saying if we draw a line parallel to x-axis, it will always intersect at one point. If we are talking about some decreasing function, we have drawn a line parallel to x-axis, it will always intersect at one point. So if any function is given to us and we are able to prove that the function is increasing or the function is decreasing in its domain, then it means that that particular function it is a 1 1 function. That is, if f dash x is greater than equal to 0 or f dash x is less than equal to 0 for every element x of the domain, then the function is 1 1. So these are also the methods to prove that a given mapping is a 1 1 mapping. The next formula now we have, it is the number of 1 1 mappings. So suppose we have two sets, one is the set A and set A has m elements, and there is another set B and the set B has n elements. Then the number of 1 1 functions from A to B, this thing we have to count. Now we know from the definition of 1 1 function that if we are considering this first element x1 from A, it will have a unique image over here in B. This is from the definition of the function, and we are saying this, suppose this y2 is the image of this x1, then the pre-image of this y2, it is only x1, that is there is no other element which can be mapped to y2. So if we have to count the number of ways in which we can do this, we are saying x1 can be mapped to n elements because the set B has n elements. Now if x1 is suppose mapped to y2, then we are next moving to the element x2. Now x2 can be mapped to any of these elements over here, and how many elements we are left with this? It is n minus 1 elements. Now next, when we are talking about this x3, it will, how many elements of B we are left with which this x3 can be mapped? It is n minus 2 elements. And when we are talking about this element m, xm, it can take n minus m plus 1 images, or we are saying it can be mapped to these many. We have option of these many elements from which it will be mapped to one of these elements. So the total number of elements that we will have, it will be n into n minus 1 into n minus 2, so on up to n minus m plus 1, and this value is equal to npm if n is greater than equal to m, and this value is 0 if n is greater than n is less than m. What is the case when n is less than m? Suppose we are saying that the set A has two elements and the set B has only one element. We are talking about the case when this set B has one element and this set has elements. So the only option that we have is that this element is mapped to this B, this element is mapped to this B. It means we can never form a 1-1 mapping. So we are saying how many 1-1 mappings are possible? There are 0-1-1 mapping possible if the value of n is less than m, and if value of n is greater than equal to m, then how many 1-1 mappings can be formed? It is npm. Now next we are listing the results related to the number of functions. So we have already seen that if a set x is given to us and it has n elements, the number of elements in x, that is equal to n, and number of elements in y, that is equal to r. We know that the total number of functions that can be formed from the set x to y, it is r x to the power n. Now from our previous result we have already seen that the number of functions that are 1 to 1 that can be formed from the set x to y, they are n, p, r, and this is when r is greater than equal to n, and we can write this npr as ncr into n factorial. So this thing is written over here in this formula, that when r is greater than equal to n, we are having the total number of 1-1 functions we have, it is ncr into n factorial, or we can write it as npr. Now the total number of functions we have, it is, we are talking about the total number of functions. We are saying if any function is there, either that function will be 1 to 1 or that function will be many 1. We are talking about any function is there, either that function will be 1-1 or that function will be many 1. So if we are saying there are total n r raised to the power n functions, and the number of 1-1 functions that can be formed, say it is npr. We are talking about the case when r is greater than equal to n. Then we are saying the number of many 1 functions that will be equal to r raised to the power n minus npr, and this thing is written over here. We are saying when r is greater than equal to n, the number of many 1 functions will be r raised to the power n minus npr. Similarly, when r is equal to n, the number of many 1 functions will be r raised to the power n minus 0, that is equal to r raised to the power n. Next, we have to count the number of constant functions. Constant function means, suppose we are talking about this is the set x and this is the set y. We are having the elements x1, x2, so on up to xn. Over here we have the elements y1, y2, so on up to yr. We are talking about the constant function. Constant function means this x1. Suppose it is mapped to any element over here, say y2. First of all, we are talking about in how many ways this x1 can be mapped. There are total r ways in which this x1 can be mapped. Once this x1 is mapped and it is given that the function is a constant function, it means this x2, this will be mapped to y1, this will be fixed, x3 will be mapped to y2, xn will be mapped to y2. So the total number of ways in which the functions can be formed, the number of functions that are there, it is equal to r. The number of constant functions we have, it is equal to r. Now next we are calculating the total number of onto functions. Now again we are talking about the set x is given and it has n elements, and the set y is given and it has r elements. So first of all we are talking about the case when r is greater than n. Look at this case over here. We are talking about, suppose this is the function x and this is the function y that we have. We are having the number the elements over here, say it is 1, 2 and 3, and the elements in the set, they are A, B, C and D. We are saying the number of elements in Y is greater than number of elements in X. Now if we map 1 to any of these numbers, suppose the 1 is mapped to B. Next, if we map 2 to any of these numbers, it may be mapped to B, it may be mapped to any of these numbers. Suppose we are saying this 3 is mapped to C. In place of mapping this 2 to B, we have mapped this 2 to A. We are saying that we can never map all these 3 numbers to all these 4 numbers. We are talking about the function, and the function has the property that we only have one image corresponding to this 1. It means that one of the elements of this A, B, C and D, it will not have a pre-image. It means if the function, if this set Y has more elements than the elements of this set X, then we cannot find any onto function. And this thing is mentioned over here, that if R is greater than N, then the number of onto functions is equal to 0. The second case we are talking about, suppose the number of functions in both the sets, they are equal. Suppose the elements over here, there are 1, 2, 3, elements over here it is A, B and C. Now if 1 is mapped to A, we are talking about, we have the function, we are calculating total number of functions that are onto over here. So in how many ways 1 can be mapped? It can be mapped in 3 ways. Either it will be mapped to A, it will be mapped to B, or it will be mapped to C. Now in how many ways 2 can be mapped now? It can be mapped only in 2 ways. Either it will be mapped to B or it will be mapped to C. Again, the reason being that the function is to be onto. If suppose this 2 is mapped to A, then we are left over here with one element, and it cannot be mapped to 2 elements because it will not be a function. It means that 2 must be mapped to one of B and C. So the number of options for 2 is 2. Now for 3, the 3 should be mapped to, if 2 is mapped to B, then 3 should be mapped to C. So that every element over here should have a unique pre-image. So the answer we are obtaining over here, it is equal to 3 into 2 into 1, that is basically 3 factorial. Similarly, if we generalize this formula for n elements, we are saying suppose there are n elements in this set, and or we are saying there are r elements in this set and r elements in this set. The number of elements they are equal, then there are total number of functions that we will have, that will be equal to r factorial. Next, the last case we will have, it is when r is less than n. We have to count the number of onto functions when r is less than n. So suppose we are considering two sets over here. These are the two sets we are talking about. The set A contains the element, it is 1, 2, 3, and the set B contains the element A, B. Suppose it contains 4 and this contains C over here. Now we have to calculate the number of onto functions. So we are saying that the number of onto functions, that will be equal to total number of functions minus number of into functions that can be formed over here. We have total number of functions. If we have any function given to us, either it is onto or it is into. It means if we have to calculate the number of onto functions, then that will be equal to total number of functions minus the number of into functions. So total number of functions we have over here, it is r raised to the power n, that can be formed from a set X to the set Y. Now we are calculating the number of into functions over here. Now to calculate the into functions, we are looking at this set y over here. Into function means that when any function is given over here, say we are talking about the first function f1, and suppose this element c does not have any pre-image. We are talking about how many cases are there. So we are saying there is a case when this element c will not have an image. We are talking about only one element, that one element is not having an image. We are saying there can be a case when this b is not having an image, pre-image. So how many ways are there? We are saying the total number of ways in which we can choose one element from this. It is RC1. That is, we are having three elements. We can choose one element from it. Now suppose we have chosen the element C. We are saying C is not having any pre-image. So what we are left with is, we are left with a set over here. It is having element 1, 2, 3, 4. And there is another set over here which is having the elements A and B. Now how many functions can be formed from this set? It is 2 raised to the power 4 functions can be formed. It means we are talking about how many functions can be formed? It is r minus 1 raised to the power n functions can be formed. So what this thing is representing? We are saying RC1 means in how many ways one element can be chosen from this? R minus 1 raised to the power n means that out of the remaining elements, if there are total 3 elements, then the number of remaining elements it is 2. If there are total r elements, the number of remaining elements will be r minus 1. And the number of functions that can be formed now it is r minus 1 raised to the power n. Now next step we are saying, again we are considering the same sets over here. We are saying this set has elements 1, 2, 3 and 4. And this second set has the elements A, B and C. In how many ways we are talking about now is, suppose there are two elements over here which are not having the pre-image. So how many elements, in how many ways this element can be chosen? It is basically we are choosing two elements. So we are writing it is 3C2. How many elements are left now? It is 3 minus 2 elements are left. We are talking about we have 1, 2, 3 and 4, and over here we are left with an element A, and number of functions that can be formed over here, that will be 3 minus 2 raised to the power 4. It means we are talking about plus NC2 R minus 2 raised to the power n. So when we continue in this way, we obtain the answer over here that when R is less than equal to n, the number of onto functions that can be made, it is equal to this. Now we have to calculate the number of into functions. So total number of functions we have, it is r raised to the power n. From total number of functions, we have subtracted the number of into functions. We have subtracted the number of into functions, and we obtain the number of onto functions. So these are the formulas for the number of onto functions and number of into functions. Now we have the problems based upon these results. So we are given, let the set X has elements 1, 2, 3, 4, 5. So the number of elements in the set X, that is equal to 5. And this set B is there, and the number of elements in this set, it is 6. We have to find the total number of functions. So total number of functions, that will be equal to 6 raised to the power 5. The total number of 1 functions, the formula we know it is 6C5 into 5 factorial, and on the answer you will obtain it is 720. Next we have to find is the total number of many one functions. So number of many one functions will be total number of functions minus number of one functions. Next we are calculating the number of constant functions. So number of elements in y it is 6. So number of constant function it is 6. Next we have to calculate is the number of onto functions, and over here we have r is greater than n. So the number of onto functions that we will be having, it is 0. Next is the total number of into functions, that will be total number of functions minus total number of onto functions, and the answer we obtain, it is 6 raised to the power 5. The next question we have is find the number of surjections from A to B, where A is equal to 1, 2, 3, 4 and this B is equal to A comma B. So we are saying the number of surjections that we will have, it is the total number of functions. The total number of functions that we will have, it is 2 raised to the power 4 minus, now we are talking about the values we have over here. We are saying the set A has elements 1, 2, 3 and 4. Set B has the elements A and B. So first of all we are talking about, if this element, if one element is not chosen over here, it means out of these two elements we are choosing one element, and we are writing it is 2 minus 1 raised to the power 4 plus 2c2 into 2 minus 2 raised to the power 4. So the answer we obtain, that is equal to 16 minus the value for this term, it is 2 minus 1, that is equal to 1, and 1 raised to power 4 is 1. 2c1, it is 2. Next we are saying it is 2c2. The value of 2c2 we have, it is equal to 1. So it is 1 into 0. So the answer 16 minus 2, that is equal to 14. So number of onto maps that we will have, it is equal to 14. Next we have is the many one mapping. So many one mapping, we have already seen the definition. We are saying, suppose we are having two sets, one is the set A and one is the set B. This element, if we look at y3 from B, we are talking about this element y3 which belongs to the set, this is the set A, this is the set B. How many pre-images it has? It has the pre-image 3, it has the pre-image 4. So we are saying this map that is given to us, it is a many one map. Second, we are talking about this function g is there. We are saying, look at this element y3 over here. To how many elements this y3 is mapped? It is mapped to x3, it is mapped to x4. So this y3 is mapped to x3 as well as x4. It means this function g is also not a 1-1 mapping, so it is a many one map. Next is fx. This function is given to us. It is fx is equal to x square plus 1. Now if we plot this function on the number line, there is no domain on range given over here. It means we are considering this function f from R to R. If we plot this function on this xy plane, we obtain the graph in this form. This is the graph of this function, x square plus x. Now if we apply the parallel line test, it means we are talking about the graphical method to check the 1-1 mapping. We have drawn a line parallel to the x-axis and it is intersecting this graph of the function at two different points. So what this thing means is that if we are talking about this value 1, the inverse image of this 1, we have 2 points. So this is the point, say x1, and this is the point x2 on the x-axis. So we are saying that f of x1 that is equal to 1 and f of x2 that is equal to 1. So there are two distinct points x1 and x2 whose image is 1. It means p-image of 1 is x1 comma x2. So this map, it is not a 1-1 map and it is a many one map. So this is the method how we check whether a mapping is 1-1 or many one using the graph. Second method we have already seen. We are talking about the function fx is equal to x square plus x. Now if we calculate the value of derivative of this function, we have it is 2x plus 1. Now we are trying to find the points where this function is greater than 0. We are saying 2x plus 1 is greater than 0 if x is greater than minus 1 by 2, and 2x plus 1 is less than 0 if x is less than minus 1 by 2. So it means this function is neither increasing nor decreasing. So this is not a monotonic function, and hence it is a many one function. Monotonic means we are talking about a function is monotonic if either it is increasing or it is decreasing. And this is not a monotonic function, hence it is not a one function, and hence it is a many one function. Next we have is the onto mapping or a surjective map. And we have already seen the definition of onto mapping. So we are saying a mapping is onto or it is surjective if there is no element in the codomain. We are saying suppose a function f is defined from a to b, then we are saying there is no element in the codomain b which does not have a pre-image in a, or we are saying that the range of f that is equal to codomain of this function f. Now suppose we are talking about the polynomial function px, say it equal to x, or we are talking about the polynomial function that is equal to x cube. So in this first case we are saying the domain of this function p, they are defined from R to R, the codomain it is R. Now what is the range of, say this is the function p1, this is the function p2. So the range of the function p1 that is equal to R, and that is equal to the codomain of this function. Similarly the range of the function p2 that is equal to R, that is equal to the codomain of this function. So what we are looking from here is, we are saying we are having the result that any polynomial function of odd degree, we have any polynomial function of odd degree, it has the range as the real numbers, so it is always an onto function. Next we have is this function fx is given, it is x minus 1 into x minus 2 into x minus 3. We have to prove that this function is surjective but it is not injective. It means this function is onto but not 1 1. Now if we look at this function fx, we are saying this is x minus 1 into x minus 2 into x minus 3. Clearly this is a polynomial. If you multiply these terms, you will get a polynomial whose degree is 3. It means this is a polynomial function of degree 3. 3 is odd. It means this function is an onto function because the range of this function f that will be equal to the codomain that is R, real numbers. Now we are saying we have to prove that this function is not 1 1. So if we talk about the value of this function, if we are looking at the value of f of 1, the answer we have it is 0. If we are talking about the value of this function at 2, the answer is 0. If we are talking about the value of this function at 3, the answer it is 0. So what we get from this is that the pre-image of 0, we are saying pre-image of 0 that is equal to the set 1, 2 and 3. It means the pre-image of the element 0, it is not unique. It means this function, it is not 1 1. 1 1 is also called injective. So this function is not injective. Next is if f is defined, is a function defined from the real numbers to the set pi by 2 to pi by 6 to pi by 2, and fx is defined like it is sine inverse of x square minus a over x square plus 1. We have to prove that and it is given that this function is an onto function. We have to find the set of values of a for which this function is onto. Next we are given a function f that is defined from R to closed interval minus pi by 6 to open interval pi by 2, and the function fx is defined like sine inverse of x square minus a over x square plus 1, and it is given that it is an onto function, and we have to find all the values of a for this function fx it is onto. So for this function to be onto, we are saying that the range set of this function, that should be equal to this. It means the value of sine inverse of x square minus a over x square plus 1, this should lie between pi by 6 to pi by 2. So this thing implies us that 1 by 2 is less than equal to x square minus a over x square plus 1 is less than 1. Now to this numerator part, we are adding 1 and subtracting 1, and we can write this numerator as x square plus 1 minus, we have written x square plus 1 minus a plus 1. So this thing implies us that 1 by 2 is less than equal to x square plus 1 over x square plus 1 minus a plus 1 over x square plus 1. Now this x square plus 1 get cancelled, we are left with this 1, and this is less than 1. So what we have obtained over here, it is 1 by 2 is less than equal to 1 minus a plus 1 over x square plus 1 is less than 1. So this thing implies us that minus 1 by 2 is less than equal to minus a plus 1 over x square plus 1 is less than 0, and this thing implies us 0 is less than a plus 1 over x square plus 1 is less than equal to 1 by 2. It means we are saying that the value of, look at this term over here, x square plus 1, this term it is always positive, and we want this term to be positive. We want this term to be positive. So on solving these first two parts we are talking about, we will obtain that a plus 1 is greater than 0. So this implies us a is greater than minus 1. So this gives us that the value of a lies between minus 1 and infinity. So if the value of a lies between minus 1 and infinity, we are saying this function will be an onto function. Now the next, we have given some examples of the functions along with their graphs to check whether these functions are bijective or not. So the first function that is given to us, it is fx is equal to mod x. We have drawn the graph of f mod x. This graph we already know that this is the graph of mod x. So we are saying we have drawn a line parallel to x-axis, and we can see that this line intersects this graph at 2 points. It means this function, it is not a 1 to 1 function. Now the second thing we have is, if we are talking about this function fx is equal to mod x, and we are writing this function is defined from R to R, then what we will have, that for these values, for negative values of y, there is no pre-image present. It means for the range, if we consider the code name as R, then this function is neither 1 nor onto, that is, it is neither surjective nor injective. But if we are considering the code mean, to be the interval 0, infinity, then this function will become onto function. Next we are talking about the function, it is fx is equal to x into mod x. Again this function f, it is defined from R to R. Now the graph of this function, it is as shown over here. This is the graph of this function, and it will continue infinitely like this. So if we draw a line parallel to x-axis over here, it will always intersect this graph at one point. It means this function is 1 to 1. And second thing we have is that there is no value of y for which we cannot obtain the corresponding value of x. If we are considering this value of y, we can find the pre-image corresponding to this value of y over here. It means this function is also onto, and 1 onto function, it is called a bijective function, or it is called 1 correspondence. Next we are talking about the function, it is fx is equal to x cube. So this is a polynomial function of degree 3. If we plot the graph of this function, it will be like this. If we draw a line parallel to x-axis over here, it will always intersect at one point. The graph of this function will continue like this. It means that for every value of y, we will obtain a value, the pre-image over there, that there always exists an x such that f of x is equal to y for all y belongs to R, or we are saying the range set of this function that is equal to R, that is equal to codomain of this function. So this function is also a bijective function. Next function we are talking about, it is fx is equal to sine of pi x by 2. Now we are saying if this function is defined, even over here that domain is to be noted, it means we are talking about if this function is defined from the interval say minus pi by 2 to pi by 2, or we are talking about if we are restricted to this graph over here, we are saying this function is defined say in this region only, that is it is defined between the values over here, or we can restrict its domain to be minus pi by 2 to pi by 2, then in this region this function is a bijective function. If we draw a line parallel to x-axis, it is intersecting the graph of this function at only one point. The second thing we have is in this region, when we are talking about this region from minus 1 to 1, if we consider the range of this function to be minus 1 to 1, we are talking about this function f that is defined. It is defined from minus pi by 2 to minus 1 to 1. Then this function is bijective. We have to find, we are talking about that if this function f is defined from this to this, it is bijective, but if this function is defined from R to R, then this function is not bijective function. Now next we have the function fx is equal to x square is given, and it is given that the domain and codomain of this function, it is from R to R. We have to prove that this function is neither 1 nor onto. So one method we have already seen, it is using the graph of this function. Now we are not using the graph over here, but we are manually showing over here that this function is using the definition. We are saying, we are showing over here that this function is not 1 and onto. So if we look at this function, we are saying the value of this value f of 1, that is equal to 1, and that is equal to f of minus 1. So if we write the inverse image of the element 1, we write the inverse image of the element 1, then it is 1 as well as element minus 1. So this thing shows that 1 does not have a unique inverse image. 1 belongs to R and it does not have a unique inverse image. So this function is not a one-to-one function. Next is, we have to prove that this function is not onto function. So we are saying out of this range codomain, we are considering an element say minus 1, and we are saying that fx is not equal to minus 1 for any x belongs to R. We are saying, what this thing means is, we are saying that x square cannot be equal to minus 1 for any x belongs to R. It means the range set of this function f, that is equal to 0 to infinity, and this is not equal to R, that is equal to the codomain of this function. It means this function is not an onto function. So you can use any of these methods You can also use the graphical method over here. We are drawing the graph of this function. We are saying the graph of the function y is equal to x square. It is like this. You draw a line parallel to x-axis. It will intersect at 2 points. So we are saying this function is not 1 1. The range of this function from here we can see it is 0 to infinity, or we are writing for -1. If we take y is equal to -1, there is no value of x for which f of x is equal to -1. So this function is not an onto function. So you can use any of these methods. Next is the function fx is equal to mod x, and we have to prove that this is neither 1 1 nor onto. And this function we have already seen that it is of this, the graph of this function, it is in this form. Again, if we draw a line parallel to x-axis, it will intersect at 2 points. It is not 1 1. For the value -1, for y is equal to -1, there is no x for which f of x is equal to -1. So we are saying this function is not an onto function. If we are not using this graphical method, we can manually calculate these values. We are saying that f of -1, that is equal to mod of -1, that is equal to 1, and that is equal to f of 1. So the inverse image of 1, or pre-image, we are saying in place of inverse image we are using the word, it is pre-image of 1, that is equal to -1 and 1. It is not unique, so this function we are saying it is not 1 1. Second thing, we are saying that -1 belongs to R, has no pre-image in R. It means that this function is not onto function. Next, we are talking about for any real number x, the greatest integer function, and it is given that it is function from R to R. So if we plot the graph of this function, we know that the graph of this function is of this form. So if we draw a line, we are drawing a line parallel to x-axis, and it is passing through, say, the point 1, then clearly it is intersecting at different points over here. So what we are trying to say from this is that if suppose I am considering the point over here, say it is 1.2, and I am considering another point 1.3. So what is the greatest integer function of 1.2? It is 1. What is the greatest integer function of 1.3? It is 1. So we are saying that there are different elements in x or R. That is, we are talking about the image of 1/2 and image of, we are talking about image of 1/2 and image of 1.3. They are same. So it means this function is not a 1 1 function. This thing is also clear. If we draw a line parallel to x-axis passing through the point 1, or we are drawing a line passing through the point 2, then we can see that this line, it intersects the graph of this function at infinitely many points. So this function is not a 1 1 function. Now second thing we have is the range of this function, that is equal to the set of integers that is not equal to the codomain. The codomain we have, it is R. So in place of this R, if it is given the set Z, then this function will become an onto function. But over here this function is not an onto function because the range set and the codomain, they are not equal. So this function we have proved that this is neither 1 1 nor onto function. Next is let R0 be the set of all non-zero real numbers. R0 be the set of all non-zero real numbers. We have to prove that the function f defined from R0 to R0 and fx is equal to 1 by x is a 1 1 onto function. So to prove that it is a 1 1 function, we suppose that f of x1, that is equal to f of x2 for two numbers x1 and x2 we are talking about. Then this thing implies us that 1 over x1, that is equal to 1 over x2, and this implies us that x1 is equal to x2. So we are saying that if we are talking about two elements fx1 and fx2 from the range set or the image set we are talking about. If these two elements, these are equal to each other, then this thing will imply that the two elements x1 and x2 whose image are these fx1 and fx2, they are also equal to each other, and this gives us that f is a 1 1 function. This is how we prove that a function is 1 1. Now next thing we have to prove is that this function is an onto function. So to prove that it is an onto function, we are writing this function, it is y is equal to 1 by x. So this implies us that x is equal to 1 by y. Now if y is not a real number, then we are talking about the domain and range of this function. We are calculating. We are talking about this function fx is equal to 1 by x. We are trying to calculate the range of this function. So we have equated this function 1 by x, this value 1 by x to y. We have obtained that x is equal to 1 by y. So we are saying we have obtained another function. It is f of y is equal to 1 by y, and this function f of y, this is the inverse, basically the inverse function of this function fx, and we know that the domain, suppose we are writing it is g of y, and we know that the domain of the function g, that is equal to range of the function f, and range of the function g, that is equal to domain of the function f. Now look at this element over here, g of 1 by y. So what is the domain of this function? That is equal to r0, and that will be equal to range of the function f. And what we obtain is, what we are given over here is that the codomain of this function is r0. We have obtained that the range of this function is r0. So codomain is equal to range. So we are saying that this function is an onto function. So to prove onto function, we have basically shown that corresponding to each element y in r0, we have some x in r0, which is the pre-image of this element y. Next is show that the function f defined from r to r, fx is equal to x cube, is 1 1 and onto. We have already seen that this function x cube is 1 1 onto from the graphical method. Now we are talking about the function x cube. It is 1 1 or not. So suppose we are saying that f of x1 is equal to f of x2. So we have x cube is equal to x1 of cube is equal to x2 of cube, and this implies us x1 is equal to x2. So this thing gives us that the function f that we have, it is a 1 1 function. Now to prove the onto part, we are saying we have to calculate the range of this function. So we are assuming, suppose y is equal to x raised to the power 3. So this thing implies us x is equal to y raised to the power 1 by 3. Suppose this is equal to the function g of y. Now domain of the function g, that is equal to r, and that is equal to range of the function f, and that is equal to the codomain of f. So we obtain that this function f is an onto function. Now the next function that is given to us, it is f is defined from r to r, and the definition of the function is fx is equal to 3 minus 4x. We have to show that this function is 1 1 onto and hence bijective. So we are talking about f of x1 is equal to f of x2. That's saying let f of x1 is equal to f of x2. So this thing implies us that 3 minus 4x1 is equal to 3 minus 4x2, and this thing implies us x1 is equal to x2. So this gives us that the function f is 1 1. Now next we are talking about this function f of x is equal to 3 minus 4x, if we write it equal to y, this thing implies us that 3 minus y is equal to 4x, and this implies us 3 minus y over 4 is equal to x, and suppose this is equal to g of y. Now domain of the function g, that is equal to r, and that is equal to the range of the function f, and this is equal to the codomain of the function f. So we obtain that this function is an onto function, and a 1 onto function is called the bijective function. So we have proved that this function is a bijective function. Now the next function that is given to us, it is f is defined from the set of natural number to the set of natural number, and this is the definition of the function that is given to us, that is fx is equal to x plus 1 if x is odd, and fx is equal to x minus 1 if x is even. We have to show that this function is 1 1 and onto. Now for the 1 1 part, we are considering, suppose f of x1 that is equal to f of x2. Now in this case we have three cases over here. The first case we have is when one of x1 or x2 is odd and other is even. Second case we have is that x1 and x2 are odd, and third we have is x1 and x2 are even. Now we are saying when one of x1 and x2 is odd, suppose we are saying x1 is odd and x2 is even, then the value of f of x1 that we will have, it is x1 is odd, means the value we will have it is x1 plus 1, and we are saying x2 is even, so the answer we are having it is x2 minus 1. So this thing gives us that x1 minus x2, we are talking over here, that is equal to minus 2, or we are writing it is x2 minus x1 is equal to 2. Now what we have over here is that x1 is odd and x2 is even, and we are obtaining that x2 minus x1 is 2. We are saying this thing is not possible, this is a contradiction. It means what we have supposed, this case cannot happen. This is not the case that can happen, that is x1 and x2 either they should be even. This is not the case, it means that they cannot be, that one cannot be even and one cannot be odd. Now we come to the second case when x1 and x2 are odd. When both of these are odd, then value of f of x1 that will be equal to x1 plus 1, and f of x2 that will be equal to x2 plus 1. So this gives us x1 is equal to x2. Third, we are talking about when both are even, we are getting it is x1 minus 1 that is equal to x2 minus 1. So this implies us x1 is equal to x2. So from these three conditions, we are obtaining that when f of x1 is equal to f of x2, so this implies us that x1 is equal to x2. It means the function f that is given to us, it is a 1 1 function. Next thing we have to do is we have to prove that it is an onto function. For this we have to calculate the range set over here. Now look at this function over here. We are saying suppose y is equal to x plus 1 when x is odd, and it is x minus 1 when x is even. So again we have two cases over here. First case is if x is odd, what this will imply, that y is even because y is equal to x plus 1. Second case we are talking about when x is even, then we will have y is odd. It means that the range set will be containing all even elements as well as all the odd natural numbers. So the range set of this function that will be equal to the set of natural numbers, and this is equal to the codomain of this function, that is set of natural numbers. So this function is both 1, 1 and onto. Now the next question we have is the function f is given to us. It is f from n to n, and it is defined like f of n is equal to n plus 1 by 2 if n is odd, and it is n by 2 is if n is even. Now we have to show that this function is many one onto function. So if we try to write the range of this function, the domain of this function, it is n. So we are writing the value of f of 1. So that will be 1 is odd. So the answer you will get it is 1 plus 1 by 2. That is equal to 1. If we are writing f of 2, then 2 is even. The answer you will get it is 2 by 2. That is equal to 1. When we are writing f of 3, the answer you will get it is 3 plus 1 by 2. That is 2. Then we are writing f of 4. The answer we will obtain it is 4 by 2. That is equal to 2. So likewise, if we continue, we will obtain the images of these numbers 1, 2, 3, 4 and so on. So it is clear from here that if we look at the pre-image of 1, then we are saying f of 1 is equal to f of 2 is equal to 1, and this thing shows that this function is many 1. That is, for two different elements or two different natural numbers, we have the same image 1. Next we have to prove that this function is onto function. So if we consider any element n that belongs to the codomain of this set, we have to show that there is an element in the, that is, there is a natural number for which f of that natural number that is equal to n. We have to show that for every element n in the codomain, we have an element in the domain for which f of that number is equal to n. Now we are saying, suppose that number it is m, so it means we are interested in a number. We are saying f of m, it should be equal to n. Now what is f of m? We have two cases over here, either m is odd or m is even. If m is odd, the value of f of m we have it is m plus 1 by 2, and if m is even, then the value we have it is m by 2, and we are saying this is equal to n and this should be equal to n. So the value of m we obtain, that is 2n minus 1. Over here the value of m we obtain, that is equal to 2n. So we are saying we have obtained a number. Suppose that number we are talking about, it is f of 2n minus 1. The answer for this number, it is always equal to, it is equal to n. And if we are talking about the number f of 2n, then this 2n is even number. The answer we will have it is n. So we are saying for every element of the codomain, we have an element in the domain whose image is equal to n. It means the codomain of f, that is equal to the range of f. So it means this function is an onto function. Next we have to prove that the signum function, it is neither 1, 1 nor onto. So the definition of signum function we have it is fx is equal to 1 when x is greater than 0, it is 0 when x is equal to 0, and it is minus 1 when x is less than 1. It means if we talk about the value of f of 1, that will be equal to f of 2, that will be equal to f of 3, and all these values, these will be equal to 1. It means this function is not 1, 1, it is not 1, 1. Now next thing we are talking about, we have to prove that it is not onto. The function it is defined from R to R, so it means we have to show that there exists a real number which is not the image of any element of the domain set. So suppose I am talking about 2 that belongs to R, and we are saying there does not exist any number x belonging to R for which f of x is equal to 2. So we are saying that we have an element 2 in the codomain which does not have any pre-image, so this function is not onto. The second method to prove this is that we are writing the range set of this function. the range set of this function R of f, that will be equal to -1, 0 and 1. This is the range set of this function, and this is not equal to the codomain of f, which is equal to R. So we are saying this function is not an onto function. Another way to prove this is, we are talking about the graph of this function. Suppose we are drawing the graph of the signum function. This is x-axis, this is y-axis. We are saying for x is equal to 0, the value is 0. For x greater than 0, the value of this function it is 1. For x less than 0, the value of this function it is -1. So we are saying if we draw a line parallel to the x-axis at this point over here, it is intersecting this line at infinite points. It means this function is not 1, 1. Next, we are saying there are points over here. We are talking about the codomain over here, it is R. So if we consider a point, say 1 by 2 over here, y is equal to 1 by 2, then there is no pre-image of this point 1 by 2. It means this function is not a onto function. So there are different ways to prove. You can use any of these ways to prove that this function is neither 1, 1 nor onto. Next we have is, let a is equal to r minus 3. R minus 3 means from the set of real numbers we have removed this element 3, and b is another set which is r minus 1, that is from real number we have removed the element 1, and the function f is defined from a to b, and it is defined in the form fx is equal to x minus 2 over x minus 3 for all values of x belongs to a. Now we have to show that f is 1, 1 and onto. So first of all we are talking about 1, 1. So we are writing, suppose f of x1 is equal to f of x2. So this thing implies us that x1 minus 2 over x1 minus 3, that is equal to x2 minus 2 over x2 minus 3. So if we cross multiply these two terms, so we get it is x1 minus x2, x1 minus 2 into x2 minus 3, that is equal to x2 minus 2 into x1 minus 3. This thing implies us x1 x2 minus 3x1 minus 2x2 plus 6, that is equal to x1 x2 minus 3x2 minus 2x1 plus 6. What we get is that this 6 gets cancelled. Then we are having this x1 x2 gets cancelled, and what we are left over here, it is minus 3x1 plus 2x1, that is equal to minus 3x2 plus 2x2. So this gives us x1 is equal to x2. So we are saying if f of x1 is equal to f of x2, then this thing implies us that x1 is equal to x2. So what we get is that this function we have, it is an onto function. Now next thing we have to prove is, we have to, this function fx is given to us. We are saying this function fx is x minus 2 over x minus 3. Now we have to find the range of this function. So to find the range of this function, we are equating it equal to y, and we are writing it is y minus 2 is equal to xy minus 3y. So this thing implies us, this is x minus 2 is equal to xy minus 3y. So this thing gives us x minus xy is equal to 2 minus 3y. So this gives us x is equal to 2 minus 3y over 1 minus y. This is a new function, says it is g of y, and domain of g, that is equal to real numbers minus 1, because this denominator should not be equal to 0. So we are saying the domain of this function g, it is all real numbers except 1, and that is equal to range of f. So we are saying the range of this function f, that is equal to r minus 1, that is equal to the set B, that is equal to codomain. So we obtain that this function is both 1, 1 and onto. Now next we have is, let a and b be two non-empty sets. We have to show that the function f defined from a cross b to b cross a, and it is defined as f of ab is equal to f b comma a, is a bijective function. So to prove the bijection, what we were doing, we have to consider the element x1. We are saying f of x1 should be equal to f of x2. This thing implies x1 is equal to x2. This thing we prove when we are having the function defined from a to b. Now the function it is defined, the domain of this function it is a cross b. So we are saying the elements of a cross b, they will be of the form a comma b. So we are considering the function f is there such that a1 comma b1 that is equal to f of a2 comma b2. In place of x, now we are having the element a1. In place of this x2, we are having the element a2 comma b2, because the domain of the function it is a cross b. So by applying this function, the definition of this function, we get this is equal to b1 comma a1 and this is equal to b2 comma a2. These are the ordered pairs, and by the properties of ordered pair we know that these two ordered pair will be equal if b1 is equal to b2 and a1 is equal to a2. Or we can say from this is that a1 comma b1 that will be equal to a2 comma b2. So we are, if we are considering this element as x1 and this element as x2, so basically we have proved that x1 is equal to x2. So this thing proves that this function is a 1 function. Now next we have to prove that it is onto. We have to prove that this mapping is a bijection. It means we have to prove it is both 1 and onto. So we are considering an element b comma a that belongs to the codomain of this function, and we have to prove that for each b comma a there is an element in the domain whose image is b comma a. Then we are saying if b comma a belongs to this, so this thing implies that b belongs to b and a belongs to a. It means there exists an element a comma b belongs to a comma b such that f of a comma b is equal to b comma a. So what we have proved is that for every element of the codomain there exists an element in the domain. There exists an element in the domain. This should be a cross b over here, such that f of a comma b is equal to b comma a, and this thing proves that f is onto function, and a function which is both 1 and onto, it is called the bijective function. Next we have to prove that the function f defined from R to R, and the definition of the function is fx is equal to 1 plus x square is many 1 into function. We have to prove that it is many 1 and it is into. So first of all, to prove that it is many 1, we have to show that there is an element in the codomain, there is a real number which has two pre-images. So if suppose I am talking about the number 2, so in place of talking about the number 2, we start it with, we write the image of the element 0, the answer we obtain it is 1. If we write the image of the element 1, the answer we obtain it is 2. If we are writing the image of the element minus 1, the answer again we are obtaining it is 2. I am not saying that these are the only values, because the domain of this function is R. We are just trying to find some values over here at some points so that we can check whether it is 1 or not, and we have obtained that f of 1 is equal to 2 as well as f of minus 1 is equal to 2. It means that this function is not a 1 function. Now the next thing we have is, if we are talking about 1 plus x square, and suppose we are equating it equal to y, then what we obtain is that the value of x that we have, it is equal to plus minus square root of y minus 1. So when we look at this function and we try to find the domain of this function, we obtain that y should be greater than equal to 1. So this thing gives us that the domain or the range of this function, it is 1 comma infinity. So what we get from this is, suppose I am talking about an element 0 that belongs to R. There does not exist any element x in R such that f of x is equal to 0. Similarly, we have shown over here that for -1 belongs to R, there is no pre-image in R, so f is onto. So there are different ways to prove these things. We have proved over here that this is the range set and this is not equal to the codomain of this function. So we are saying that this function is not an one onto function, so it is an into function. Next is, show that the function f defined from R to R, fx is equal to x raised to power 4 is many one and into. Now if we look at this function, it is defined from R to R. If we substitute the value f of 1, you get the answer, it is 1, and that is equal to f of minus 1. So this thing gives us that the function is many one function. Next we have to prove that it is an into function. So we are talking about an element, say -1 belongs to R. We are saying it has no pre-image. That is, for no value of x, there does not exist any x in R such that x raised to power 4 is equal to -1. So we are saying this function is not an onto function, so it is an into function. Next is, show that the function f defined from R to R with fx is equal to x raised to power 5 is 1, 1 and onto. So the function, the domain and codomain, they are R to R, and we are talking about the function fx is equal to x raised to power 5. This is a polynomial function of odd degree, so this is 1, 1, or we can say that if we consider f of x1 is equal to f of x2, then this thing implies x1 raised to power 5 is equal to x2 raised to power 5, and this thing implies us x1 is equal to x2 if x1 and x2 these are the real numbers, and this thing gives us that this function is a 1, 1 function. So you can use directly this result that for the polynomial of odd degree the function is 1, 1, or you can show that this function is 1, 1 using this result. Next we have to prove that this function is onto. So we write y is equal to x raised to power 5. So this gives us x is equal to y raised to power 1 by 5. Suppose this is equal to g of y. So the domain of the function g, that is equal to R, that is equal to the range of the function f, and that is equal to the codomain of this function f. So this function, it is an onto function. Or we are saying over here that for each y belongs to R, there exists y raised to power 1 by 5 belongs to R such that f of y raised to power 1 by 5 is y. It means for every element, for every real number, we have an element of the domain whose image is y. It means that every element of the codomain, it has a pre-image, and hence this function is an onto function. Now the next question we have is, let the function f is defined from, it is closed interval 0 to pi by 2 and fx is sin x. We have the function g defined from closed interval 0 to pi by 2 and gx is equal to cos x. We have to show that each of the function f and g is 1, 1, but f plus g is not 1, 1. So to prove that both the functions, this sin x and cos x, these are 1, 1, we are considering, suppose sine of x1, say it is equal to sine of x2. So this thing implies us that x1 is equal to x2. This is why this thing implies this, because the domain of the function that is given to us, that is 0 comma pi by 2. So it means the value of this sine of x1 is equal to sine of x2. This will give us x1 is equal to x2. If suppose the domain of this function is given to be R, then this thing will not hold, because for different values we can have the same values of sine x if the values are outside the first quadrant. Next, similarly we are saying for cos x, we are considering cos of x1 is equal to cos of x2. Again both x1 and x2, they belong to the interval 0 comma pi by 2. So this thing implies us that x1 is equal to x2. So this thing proves that both these functions, these are 1 functions. Now if we consider the function f plus g, the function f plus g of x, that will be equal to sine x plus cos x. Now we have to prove that this function is not a 1 function. It means we have to prove that there is an element in the codomain which has two pre-images. Now if we calculate the value of this function f plus g at 0, the answer we obtain it is sine 0 plus cos 0, that is equal to 1. If we calculate the value of this function f plus g at pi by 2, because both 0 and pi by 2, these are the elements of the domain, we are saying the answer we are getting it is sine of pi by 2 plus cos of pi by 2. Again the answer we are getting it is 1. So we are saying that there are two elements in the domain whose image is 1. It means that this function is not a 1 function. It is important to note over here that if this function f, it is defined from the open interval 0 to pi by 2 and g is defined from open interval 0 to pi by 2, then the answers will change. Next question we have is, show that the function f defined from n to n, it is from the set of natural number to natural number, and fx is equal to x square is 1 into function. We have already seen that if we are defining the function f from r to r and the function is fx is equal to x square, it is neither 1 nor onto. Now we have changed the domain over here, it is f from n to n. So we are considering two elements a comma b belongs to n. We are saying suppose f of a is equal to f of b. This thing implies us that a square is equal to b square, and this thing implies us a is equal to b, because both a and b, they are the natural numbers. So what we get is that f is a 1 function. Now we have to prove that it is not onto. It means we have to find an element from the codomain which does not have any pre-image. So we are saying if we consider an element 2 belongs to n, then it has no pre-image in n. It means f is an on into function. Now the next we have the function f is given and it is defined from z to z. The domain and codomain, they are z integers, and it is f of x is equal to x square. So first thing is clear to us that both these functions, these are not equal because their domain and codomain, they are not same. We have to prove that this function is many one and into. So to prove that this is many one function, we are saying we are having the elements -1 and 1 whose image is equal to 1. So f is a many one function. Now if we are talking about again this element 2 is there which belongs to z and it has no pre-image in z, so we are saying that f is into function. So what we obtain is that the function f, when it is defined from n to n and it is fx is equal to x square, this is a 1 function and it is not onto. And when the domain and codomain, they are z from z to z or z, the integers, we are saying this function it is an many one into function. Now the next question we have is, show that the function f defined from n to n, fx is equal to x cube is 1 onto function. So now the domain of the function it is n, the codomain it is n, and the function it is fx is equal to x cube. So we are considering, suppose there are elements x1 comma x2, they belong to n, then we have f of x1 is equal to f of x2. This thing implies us that x1 cube is equal to x2 cube, and this implies us x1 is equal to x2. So we are saying this function is a 1 function. Now we are saying there is an element 2 belongs to n for which there does not exist any x belongs to n such that f of x is equal to 2. It means there is an element 2 in the codomain of this function which does not have any pre-image. So we are saying this function is an into function. Now we are saying f is defined from z to z and fx is equal to x cube. We have to prove that this is 1 1 and into function. Again we are saying suppose x1 comma x2 belongs to z. Now f of x1 is equal to f of x2. This implies x1 cube is equal to x2 cube and this implies x1 is equal to x2. It means this function is 1 1 function. And for the second part we are saying there is an element 2, there is an integer 2 for which we do not have any pre-image in z, because 2 raised to the power 1 by 3, this does not belong to z. Next is show that the function f defined from R to R and fx is equal to sine x is neither 1 1 nor onto function. So this thing we have already seen using the graph of the function sine x. The graph of the function sine x is in this form. If we draw a line parallel to the x-axis, we can see it intersects this function at the graph of this function at different points. So it means this function is not a 1 1 function. And second thing, we know that the range of this function sine x, it is from -1 to 1. This is the range of the function f, and this is not equal to the codomain of the function f. So we are saying this function is not an onto function, it is an into function. So you can use the graph or you can use this result that sine of 0 is equal to 0 and sine of pi is equal to 0. It means if we look at the pre-image of this element 0, then it is not unique. It means 0 and pi have the same image. It means f of is a many one function. So we have proved that this function f sine x defined from R to R, it is neither 1 1 nor onto. But suppose if we change the domain and codomain over here, if we are writing f is defined from closed interval 0 to pi by 2 to the interval 0 comma 1 and fx is equal to sine x, then we have this function is both 1 1 and onto. Because if we plot the graph of this function in this region, we are having the graph of this function in this form. This is 0, this point it is pi by 2, this is 0 and this point it is 1. So we are saying this function will be both 1 1 and onto function, that is this function will be a bijective function. But if the domain and range we are considering it is, the domain and codomain we are considering it is R, then this function is not a 1 1 or onto function. Next, the function given to us is, it is f is defined from the set of natural number to natural numbers and it is f of n is equal to n square plus n plus 1. We have to prove that this function is 1 1 but not onto. So suppose we are considering two elements n1 comma n2 that belongs to the domain of this function. Then we are saying f of n1 is equal to f of n2. This thing implies us that n1 square plus n1 plus 1, that is equal to n2 square plus n2 plus 1. This thing implies us n1 square minus n2 square plus n1 minus n2 is equal to 0. So this gives us n1 minus n2 into n1 minus n2, it is not minus, it is n1 plus n2 plus 1 equal to 0. Now n1 and n2, these are the natural numbers. It means this term, it cannot be equal to 0. So this thing implies us n1 minus n2 is 0. So this thing implies us n1 is equal to n2. So we are saying that f of n1 is equal to n2. This implies us n1 is equal to n2. It means this function is a 1 1 function. Now we have to prove that it is not an onto function. So if we look at the value of this function, we are saying it is f of n is equal to n square plus n plus 1, and the value of n we have, it is the natural number, n is natural number. Now if we look at this function, we are saying this n square, it is always a positive number. This n is always a positive number. It means the value of this fn, this is always greater than 1. So if we consider the element 1 belongs to n, there does not exist any element m belongs to n such that f of m is equal to 1. So we are saying there is an element 1 belongs to n, means this is the element from the codomain for which we have no pre-image, or we are saying there is no element in the domain for which